Welcome to the course on computer design of electrical machine. We will have a lecture 27 today on design of brushless permanent machines part 2. So, starting with the permanent synchronous machine configuration and modeling, a permanent synchronous motor design with winding, permanent design with fundamental design relationship and exercise numerical problems and references. So, coming to permanent synchronous machines configuration and modeling. So, coming to this configuration and modeling, as observed in the past lecture, permanent machines are broadly classified as DC commutator motor drive, brushless motor drive like DC and AC synchronous, and stepping motor drive. So, here you can see the classification. One with permanent brush DC motor, then brushless sinusoidal and rectangular rod. Rectangular rod we call it the permanent brushless DC motor, and sinusoidal we have of course permanent synchronous motor and hysteresis motor and stepper motor. Now, coming to under brushless motor drive, the PMSM is categorized as sinusoidally excited motor, as you can see in the diagram, and sinusoidally excited motors are fed with three-phase sinusoidal waveform and all-phase conductor at a time and called sine wave motors or PM synchronous motor. Now, typically here is the construction of generic PM synchronous machine, as you can see in the diagram, used by General Motors for electric vehicle. I mean, like as you can see the different parts, how it looks like a winding, how it looks like a permanent, how it is a saliency typically put into the rotor part, which really enhances the characteristic of the machine typically for field weakening. So, all brushless PM motors follow an overall similar structure with respect to the construction, with differences in the permanent magnetization and electrical characteristics. So, here is a very interesting configuration where saliency torque is reasonable in addition to permanent motors like So, now the steady state modeling of a permanent motors is important to motor design, and it helps the user to make design decision with respect to the performance assessing like voltage limit, current limits, maximum torque and associated efficiency. Now, coming to steady state modeling of permanent synchronous motor, a PMSM is normally analyzed using the rotor reference frame, which has a fixed rotor aligned with the direction of permanent flux, and in general the stator winding has three-phase quantity and it can be transformed to rotor reference frame and vice versa by using Park transformation. At a constant speed, the steady state phasor diagram of PMSM can be constructed as follows. Typically, like you can say how the phasor diagram typically for magnetization of armature in D axis and demagnetizing effect in the D axis. Typically, as you can see here, the magnetizing and demagnetizing effect both are shown by providing the typically the value of your exciting current like in the two cases. So, now open circuit EMF you can call it equal to JEQ because magnets are put on direct axis. So, induced EMF in quadrature axis, that is J omega lambda PM. So, where omega is the synchronous speed and electrical speed and the lambda PM is the flux linkage due to the fundamental component of D axis flux produced by the permanent. Although there exists some D axis induced EMF associated with the leakage flux, in most cases it is negligible, especially when the stator winding is sinusoidally distributed. And from the phasor diagram of the previous slide, we can say VD equal to minus XQ IQ plus R ID and VQ equal to EQ plus XD ID plus R IQ. So, the angle delta and gamma are defined as in the phasor diagram, then the voltage and current in the motor are defined as VD equal to minus V sin delta and VQ equal to V cos delta, and ID equal to plus minus I sin phi, and IQ equal to gamma and IQ equal to I cos gamma. In the large motors, the stator conductor resistance R is negligible, hence thus we can say ID equal to VQ minus EQ upon XD and IQ equal to minus VD upon XQ. So, the complex power per phase per pole pair in the motor is now S equal to V into I conjugate, and we can keep VD plus JVQ, and I equal to we can keep I equal to minus I conjugate we can keep ID minus JIQ, and then solving it becomes equal to VD ID plus VQ IQ plus J VQ ID minus VD IQ or equal to P plus JQ, and from this we can call it the real power is P equal to VD ID plus VQ IQ equal to VD and putting a value of ID, that is VQ IQ upon XD, and minus your VQ and value of IQ is minus VD upon XQ. and that becomes equal to V2 minus EQ upon XD plus XQ minus XD divided by XD XQ VD into VQ, and that becomes VT into EQ divided by XD into sin delta plus XD minus XQ into VT square upon 2 XD XQ into sin 2 delta, where VT equal to under root VD square plus VQ square. So here we have a two component. One is due to magnetic excitation because EQ is produced because of magnetic excitation, and the second is the saliency because of the difference in XD and SQ. So we have saliency power or reluctance power, and we have excitation power. So assume that there is no loss, then the total output torque for three phases with P pole pairs is equal to 3P upon omega into capital P, and that's a 3P upon omega in bracket VTQ sin delta upon XD plus XD minus XQ into VT square divided by 2 XD XQ into sin 2 delta. So in pure reluctance motor, reluctance synchronous motor, EQ equal to 0, so T is equal to 3 P upon omega P, so that becomes 3 P upon omega XD minus XQ VT square upon 2 XD XQ into sin 2 delta. And for general PMSM, LD is almost the same as LSQ, thus the reluctance torque is cancelled. So in PMSM, LD is lower than LQ because of magnetic flux flowing along the D axis has to cross through the magnet cavity in addition to the rotor air gap, and where the magnetic flux of Q axis only crosses the air gap. So the period of reluctance torque is 1/2 of that of the PM generated torque. So the IPSM, that is interior permanent synchronous motor, can achieve higher torque than the surface mounted PMSM, which does not have any reluctance torque component. However, the appearance of reluctance torque does not mean that the IPSM can have a higher power density than the surface mounted PMSM, because the magnet flux linkage in IPSM is not the same as that in the surface mounted PMSM with the same magnet volume. So total torque of IPSM is increased with the saliency of the rotor. You can clearly see how the torque angle versus power characteristic in IPSM. So you have reluctance torque, you have a PM torque, and then you have addition of the two with the red color line. So now you can call it the torque equation is equal to 3P by 2 in bracket lambda PM IQ and plus LD minus LQ into ID IQ. And in this expression, you can clearly see an interesting feature that, the second term is responsible for below base speed. We can increase the excitation by introducing the value of ID, and by going to be above speed, we can introduce the ID value with the opposite sign, and that do the field weakening. So that's very useful for electric vehicle with a high starting torque, and then to get a constant power characteristic over a wide range for very high substantial speed. Since magnet are put into the flux barriers, so its machine is just have a very robust construction to achieve high speed. And then coming to T as a per unit value T base, so we can call it cos delta minus eta minus 1 by 2 into I upon I base and into delta. The T base is PM torque at I base, and eta equal to LD upon LQ, that is saliency ratio, and I is the input current. So you can call it eta term is called saliency factor, and generally cannot be more than 3. So the optimum commutation may have advanced from 90 degree, the optimum commutation angle of PMSM towards 135. So torque equation show that the inductance term is important determining the output torque of an IPSM. So the circle diagram on the current vector plane is the most convenient method to explain the speed limit of PMSM, and the circle diagram can be constructed by the following equation: VD equal to minus IQ and VQ equal to SD ID plus your EQ. So if the input voltage VT is there, then VT equal to VD square plus VQ square, or equal to XQ IQ square plus EQ plus SD IQ square. Or we can say ID plus EQ upon XD square plus XQ upon XD square IQ square equal to VT upon XD square. And using inductance term, we can say ID plus lambda PM upon LD square plus LQ upon LD square into IQ square equal to VT upon LD square into 1 upon omega square. So the ellipse equation in DQ current plane is drawn at given constant input voltage VT. The ellipse shrinks towards the point minus EQ XD and 0 at the speed omega increases. As you can see here, how with the increasing speed it sinks to the point which is put with the notation of increasing omega like. So the circle diagram of IPSM on the DQ axis shown here like. So you can say the red circle are the current limit circle of which the radius will increase by enhancing the maximum current capability, and the point A typically in the diagram is the current vector position for the maximum torque at a given speed, and the point B typically the intersection between the current circle and the negative t-axis, and the ellipse can be shrunk until it is tangent to the point B and the motor has its ideal maximum speed at this point. So the optimum field weakening capability of machine is at the center point of the ellipse, and this point is also called characteristic current of an IPSM, and the give as follows: ICH equal to EQ upon XD equal to lambda PM upon LD. So at the point B, ID equal to minus Imax and IQ equal to 0. Thus the ideal maximum speed can be expressed as minus Imax plus CH I square equal to Vt upon LD square into 1 upon omega square, or omega max equal to Vt upon LD in bracket ICH minus Imax. So if ICH less than Imax, then the machine can have an infinite speed ideally, although most IPCM have the value of ICH higher than the maximum current of the inverters which feed the current into the motor. As a machine designer will try to reduce the value of ICH as much as possible for higher speed application, and as expressed in the definition of characteristic current, the lower value of ICH can be achieved by reducing the d-axis flux linkage from the rotor or increasing the d-axis in inductance value. Now coming to PMSM design. So now typical example with the MF starting from basic of winding design. So MF of a coil. So consider the stator with one turn of a coil, air gap, and the rotor shown here to illustrate the concept of MF of the winding, as you can see in the diagram. So magnetic flux produced by the coil has a distribution resulting in a north and south pole, as you can see in the typically in the diagram. And the MF axis is leading the physical coil A dash by electrical 90 degree, and assuming that the rotor and stator iron have a infinite permeability, then it is easy to realize that the MF produced by the coil is entirely spent to overcome the reluctance of the two air gap in the path of flux in a rotating machine. So instead of only one turn, if the coils has a TPH turns, then the total MF is TPHI in unit of ampere turns, where I is the current in the coil, and the MF versus rotor angle position can be drawn with a convention that positive MF is required to produce in north pole and a negative MF for the south pole. Only one half of the coil MF is utilized to produce the one pole. Thus the coil MF versus hysteresis petal position is shown here as the MF diagram. An MF with the air gap position for a single coil. Now coming to sinusoidal flux MF distribution, the MF produced by a coil has a rectangular distribution with the dominant fundamental component, but it is also rich in harmonics that are significant in comparison to the fundamental component, and the harmonics do not contribute to the useful torque and in addition produce only the losses. Hence, it is important to minimize the harmonics in the stator MF. So there are two ways to achieve it, and they are described in following. First is the typical concentrated winding. So a sinusoidal MF distribution can be achieved by sinusoidal distribution of the winding in the slot, but with the different coil pitches within a pole pitch. So such a coil arrangement is known as concentric winding and shown in the next slide for its MF diagram. And the coils MF of the coils 1 dash, 2 dash, and 3 dash are represented such that without division by 2, and it's useful case because these coils produce only one pole, thus deriving the flux across only one air gap. You can just see how the typically the MF comes typically rising and falling with the current direction, and with the how it is a concentric winding of the particular phase as it is shown in the diagram. Coming to typically the phase displacement between the MF is the same as the spatal displacement of the coil, and resultant MF of phase is the sum of total of individual coil MFs, and the resultant MF is multi-step and approximately closer to a sinusoidal. And if there are infinite slots, then the MF distribution will be triangular. But by varying the number of turns, a closed sinusoidal MF is obtained, and the coil pitches are less than the pole pitch and decrease for the coils as they progress from outer to inner slot. And the advantage of the concentric winding are easy of manufacturing and its ability to provide the nearly sinusoidal MF diffusion. And the disadvantage that the effective turns are slightly less than the algebraic sum of the turns in the coil. So consequently, a machine with this winding is saddled with the added copper weight and volume and resistive losses compared to some other winding types. Now coming to distributed winding. So in this form of winding, the number of conductors in each slot is the same as also the coil pitch is also constant for all the coils. Both of these features are in sharp contrast to the concentric winding, and distributed winding is shown in the next slide. There are 5 slots per pole per phase, and its coil carries a positive current I under the one pole and negative current minus I in adjacent pole. And you can see how really the MF there typically of the coil and how the winding is shown in the typically in the stator of this distributed winding, and the MF with the 5 coils in adjacent slot. And you can just see with the different coil MF added together, it goes to closer to the sine wave. So now the MF of the coils in each connecting pair of the slots is drawn as a rectangular with the magnitude of 0.5 Ti, positive for the first 180-degree electrical and the negative for next 180-degree electrical. As a resultant, MF of the phase coil is derived from the summing the individual MF of the coils. And the advantage of this distributed winding are better utilization of the slot volume and the higher effective turns of the winding. And it has the disadvantage of the lower copper utilization resulting from the longer end turns and higher resistive loss. Coming now to induced EMF, as the coils in the stator experience a change in the flux linkage caused by the moving magnets, so there is an induced EMF in the winding, and the waveform of the induced EMF is very dependent on the waveform of the flux linkage, and the flux linkage are the product of the flux in the air gap and the number of turns associated with the flux line. And the air gap flux is directly influenced by the rotor magnet flux density and the configuration of stator, air gap and the rotor construction. And if the rotational speed of the magnet is in electrical radiance is omega r and the air gap flux is sinusoidal, then it can be expressed phi equal to phi m sin omega rt. And given the number of turns per phase TPH, then the flux linkage are equal to your product TPH into phi, and the induced EMF is equal to the rate change of the flux linkage, and it derive equal to minus d lambda upon dt equal to minus TPH d phi upon dt equal to minus t omega phi m omega r cos omega rt or equal to minus 2 pi t ph phi m fr cos omega t. So RMS value of the induced EMF is given by equal to 2 pi t ph phi m fr under root 2 or equal to 4.44 t ph phi m into fr, where fr is the frequency of the induced EMF or rotational frequency, and a number of observations are made based on the induced EMF, this EMF equation, and are given the next couple of slides. So the EMF is proportional to the product of rotational frequency and air gap or the mutual flux, assuming that the entire air gap flux is linking the stator and the number of turns is constant. So this equation also gives the basic concept behind the control of the machine. Assuming that the air gap flux is constant, it is seen that the EMF is influenced only by the rotational frequency of the synchronous machine. Now, therefore, the excitation frequency of the voltage directly controls the speed of the machine, and which also lends itself to very precisely speed control, as the excitation frequency in the stator can be manually regulated. Beyond a certain speed known as base speed, an increase in the stator frequency will entail voltage demand exceeding the supply capability. So during that operation, keeping the voltage constant and increasing the excitation frequency reduces the air gap flux and thus allowing to go to higher speed over the above the base speed. This operation known as flux weakening. To obtain a sinusoidal voltage, it is important to have sinusoidal distribution of flux in the air gap, and this is achieved with the rotor magnets pole shaping. And if the air gap flux contains harmonic component, thus distorting the air gap flux from the fundamental sinusoid, then the quality of the induced EMF waveform is poor, and stator slot contribute to these harmonics. And you can see clearly how some example of physical permanent shaping to improve the sinusoidal profile of air gap flux density. Starting first, as you have a segment how magnets are put, and then the magnet shapes are there, and how physically you have a magnet shaping in a either center line with the butterfly and axial direction laminations, and with the central with the third harmonic shaped magnet, uniform magnet thickness along with the radial axis like orthon. Now coming to induced EMF equal to TPH phi m FR under root 2 equal to 4.44 TPH phi m into FR. So it is assumed that in the derivation that the number of turns per phase is TPH, and in final expression it needs to be modified to take into account for conductor distribution over the number of slots, for having a coil pitch other than the pole pitch, and for skewing the stator to mitigate some harmonics in the air gap MF. So it is incorporated to modify the actual number of turns with the effective turns with the help of factor known as winding factor. And for example, a 3-phase machine with 1 coils per phase and 2 rotor poles is shown on the next slide to show the induced EMF induction, and the 3-phase windings are respectively displaced by electrical 120 degree from each other. And if the mutual flux, that is air gap flux neglecting leakage flux, is plotted for the current position, then it produces a magnetic flux linkage with the phase A winding. Assuming that the mutual flux is sinusoidal, then the air gap flux density BGS and the magnetic flux linkages for the 3 phases are plotted. So you can clearly see how it is the typically simple 3-phase machine with sinusoidal flux density with the 3-phase winding in the diagram, and simple 3-phase machines with variables shown the 3 induced EMF and 3 flux linkage with the flux density shown all the sinusoidal distribution. So now coming to typically for the winding, note that the phase shift between the flux linkage and is the same as the winding phase shift, and the induced EMFs are obtained by taking the derivative of the mutual flux linkage. And they are a set of 3-phase balanced sinusoidal voltage and the corresponding to the PMSM. And suppose that the mutual flux density is rectangular, then the waveform of the machine variables are derived as they are shown here. And note that this case corresponds to PM brushless DC machine. So here you can see how typically the flux density and then the flux linkage, and how the induced EMF you have a typically of your kind of a square wave. So the 3-phase machine induced EMF and flux linkage for rectangular flux distribution. Now the mutual flux linkages are triangular, and hence the induced EMF are rectangular, resembling the shape of the flux density. And if the phase winding occupy more space than the 1 slot per pole, say for 2 slots, then the rectangular induced EMF of the coil in the adjacent slot will be connected in series to provide the final phase voltage. And in that case, the voltages will have 0 magnitude for the overlap period covering the slot angle, but double in magnitude for the rest of the duration. And this kind of winding is prevalent in permanent brushless DC machines. Now coming to winding distribution factor. To obtain the desired EMF distribution, such as sinusoidal distribution, it has been seen that the winding is spread or distributed over the number of slots, and this case was illustrated and discussed in the previous section. Such a distribution of coils in various slots to obtain a single winding has a direct consequences on the induced EMF as well as on MF. So that the slot pitch is the mechanical angle between 2 slots multiplied by the pole pair so as to express the slot pitch in electrical degree. And consider a winding phase with the 3 coils distributed over the 3 slots under each north and south poles, and it is taken that they are connected in series. So when voltage induced in the 2 adjacent slot coils, which are 2 phases with the phase shift of the slot pitch, are added to obtain their resultant voltage, note that it is less than the algebraic sum of their induced individual magnitude. The same applies to any number of the coils spread over a number of slots, such as the 3 in this illustration, and consider the slot pitch is your gamma in electrical degrees, and the induced EMF in the 3 coils sides with the series connected coils are E1, E2 and E3, and note that these voltages are equal in magnitude. Note that these EMFs are phase shifted from each other by a slot angle, and their resultant voltage, which is less than their algebraic sum of the coil voltage, is obtained by phasor summation shown here. As you can see here, typically like a voltage E1, E2, E3 at the angle, different angle of gamma as a slot angle, and you can see the total E is not an algebraic sum of E1, E2, E3. However, E1, E2, E3 are all equal. So this is the effect of winding distribution, that your EU get less than E less than 3E. So now let the induced EMF in the slot turns of the winding is E1, and likewise for the second slot is E2, and for third slot is set is E3. And such a turn or turns in the slot is connected in series with the turns in adjacent slot, and so on for that phase winding. Then the attenuation factor named as distribution or the breadth factor can be derived as the ratio between the phasor sum and the algebraic sum of the coil voltage. As you can say KD equal to sine Q gamma divided by 2 divided by q sine gamma by 2, where the q is the number of slots per pole per phase and the product q gamma represents the total breadth of the coil of a phase under one pole. In the illustrated case, here q equal to 3. So now coming to winding distribution factor, the distribution of the winding consequently carries over the harmonics component of the MF and induced EMF, and note in that case the distribution angle becomes proportional to the harmonics of fundamental frequency, and accordingly the distribution factor for the harmonics of the order of n may be derived from the fundamental distribution factor as kdn equal to sine and q gamma by 2 divided by q sine and gamma by 2. So typically the following table shows the distribution factor for various slots per pole per phase, including the harmonics. So here you can say distribution factor for various slot per pole per phase, and you can say harmonics for typically starting from 1 to 11. I mean, you will not have a typically the even harmonics, only odd 1, 3, 5, 7, 9, 11 are there, and short per pole per phase you can see if it is a 1, then you have a winding factor for certainly 1, but if you have a 2, 3, then accordingly the winding factor changes. And you can say for, of course, for fundamental it's quite dominant, order of 0.9, more than 0.95 or so. So far, then another factor is the winding pitch factor. So far it was assumed that the coils are connected in series that are spatially apart from by electrical 180 degree and the same as the pole pitch, and the desirable outcome of such an arrangement is that the coil sides generated voltage of opposite polarity under a north and south pole, which when connected to in series give a resultant of twice the conductor induced EMF, as the pole phase difference between the induced EMF is 180 degree. And if for some reason the conductors that are connected in series are not exactly spatially apart from by pole pitch, then the induced EMF has a phase shift more than the pole pitch, which leads to a resultant that is less than their algebraic sum. So this is accounted for attenuation factor known as pitch factor, and it is done as follows. You can see here typically that one coil side is a E plus and another coil side they have a E minus, and that is at angle your eta, which is not 180 degree. If it is 180 degree, it will be algebraic sum of the two EMF, but if eta is less than 180 degree, certainly it is also vector sum, which is lesser than, certainly you can call it E plus, or even vector sum is your AB is less than your AO plus OB. So if the coils are not separated by 180 degree electrical, but by eta, which is the coil pitch, then the voltage induced in the coil pitch under the south pole will be phase shifted by 180 minus eta, and it is the angle by which the coil is shorted, that is by the amount its displaced is reduced from 180 degree, and this is shown in the figure for a turn under north and south poles with the coil pitch shorter than the pole pitch, and here the resultant voltage in the shorted coil turn of the winding is shown in the figure. You can say the attenuation due to the pitch factor is derived as Kp equal to sine eta by 2, and the winding arrangement under the discussion is known as a fractional pitch winding. A shorting is used to reduce the or to eliminate the harmonics in the induced EMF, and also to minimize the length of the end turns required to connect the coils in series between the north and south pole. Now minimization of end turns length also reduces the amount of the copper and winding resistive losses, and the coil pitch for the nth harmonics is equal to the nth time the actual coil pitch, and therefore the pitch factor for the nth harmonic given by Kpn equal to sine n eta by 2. Elimination of particular harmonics is achieved by choosing the coil pitch such that the pitch factor for that harmonics is equal to 0. So for example, considering a coil pitch of 120 degree, which may be expressed as 2/3 of the pole pitch, or simply by 2/3 coil pitch, elimination of all triple harmonics such 3rd, 6th and 9th, but in the process fundamentally 86.6 and 5th, 7th, 11th harmonics have the same pitch factor as the fundamental. Likewise, 4 by 5th coil pitch eliminate the 5th harmonics, and multiply 6 by 7th coil pitch eliminate the 7th harmonics, and 11 by 10th by 11 coil pitch eliminate the 11th harmonics as shown in the table in next slide. So you can see how it is the sum of the harmonics you see here, it is 0 in the table with the different coil pitch, like with the 2/3, 4, 5th, 6, 7 and 11. So you can see by 10 by 11, 11th harmonics is 0. So that gives you an idea that how typically pitch factor are responsible to eliminate the sum of the harmonics. Now coming to skew factor. The stator windings are placed in the slot that are skewed by a half a slot or a slot pitch over axial length and accommodated by a skewing stator. And here you can see how the skewing stator is the physical diagram of skewing the stator, as well as how it is by the angle theta sk, for the skewing like. So the winding is skewed so that the certain harmonics in the induced EMF are eliminated, and for mostly the mitigation of cogging torque that is generated in the machine due to the effect of slotting. And in that process, it also reduces the resultant fundamental voltage and other harmonics. The effect of progressive skewing along with the axial length of the coil side can be determined as follows. So here typically angle of skewing, and you can see how it is the typically the sum ER as a phasor sum again of the different voltage. So if the length of the coil side is divided into very small segments, then the voltage induced in the segments are displaced from each other by a small phase shift corresponding to the skew angle and dividing the number of its segments like. So here is the resultant voltage in a coil side in a skewed stator. So the segment voltage in the coil sides on the arc of the circle subtended with the phase shift angle and the resultant voltage ER then is seen to be that of the chord as shown in the below, and according to the attenuation factor associated with the skewing, it is given as ksk equal to 2 sine theta sk by 2 divided by theta sk, or equal to sine theta sk by 2 divided by theta sk by 2, and distribution pitch and skew factor reduce the allowable voltage in the phase winding. So now coming to winding factor, overall the effect of the induced voltage and MF is shown here in the form of signal flow diagram. So coming to arithmetic sum of induced EMF in all the coils of phase winding, with the distribution effect, then the fractional pitch effect and the stator slot pitch effect, and comes the resultant of effective phase shift. So you have a typically, if we call it initially, it is a M eta 1 as a sum of the algebraic sum, then through distribution factor reduces, then pitch factor also reduces, then the skew factor also reduces, and finally you get the E value at the induced EMF in the finally across the terminal. The effect of pitch, distribution and skew factors are responsible to reduce the fundamental induced EMF in the winding. So the effect due to skewing, pitch and distribution factors are combined into a single variable term as winding factor, and that is given here k omega equal to kd, kp and ksk, and equivalently the effective number of turns in the phase winding can be thought or as attenuated by the winding factor, and then that of effective turns are substituted in the EMF equation. Therefore, the induced EMF for the actual TPH turns per phase is given equal to 4.44 K W TPH phi m Fs equal to 4.44 T phi m Fs, and where the effective turns per phase T is given equal to T equal to KW into TPH, as the fundamental is only the of interest at this time. Assuming that there is no skewing, the pitch and distribution factor are calculated for fundamental and then used to obtain the winding factor for the fundamental, and the harmonic induced EMF are calculated by substituting the respective winding factor for the harmonics as k omega n equal to kdn into kbn, and likewise the effective turns for the harmonics are computed by the multiplying the harmonic winding factor the turns per phase. Now coming to typically, having seen the implications of distribution and variation of coil pitch of winding, it is appropriate at this stage to become familiar with the some types of winding commonly found in practice in PMSN, and coil belonging to different phases can share some of the stator, and single layer windings have only one phase coil in any slot or do not share the slot with any other phase coil, and if two phase coils share a slot, then it is a two layer winding, and three layer winding with the three phase coils sharing slot may be found also, and single or multi layer windings can have a fractional and push pull coil. An illustration of the single layer full or fractional pitch coils and likewise the two layer windings are given in the following figure. So you can just see here a single layer winding, a simple 2 pole 6 slot 3 phase machine with full pitch single layer winding is shown below with the phase spread and winding diagram. So well, in single layer we can have a 160-degree phase spread only as it is shown in the winding. So single layer winding with the full pitch coils of a 3-phase machine. Here schematic layout, winding diagram, single conductor per slot, or winding diagram with multiple conductor per slot. And you can see how physically the single layer winding looks like, typically coil 1 and coil 2, and typically the head and typically the terminals are there. So now the slot pitch is 60 degree and the phase spread is the same as shown above, and note that the subscript S indicates the start of terminal of the phase and the subscript F indicate the end of the terminal of the phase. The arrows indicate the induced EMF direction, and note that the distribution factor for this winding is 1, and so also for the all harmonic. And that is the disadvantage of the machine, and hence it is rarely used in PMSM, but it is quite advantageous used in low cost PM brushless DC machine to generate the temperature induced EMF. A 2-pole 12 slot 3-phase machine is considered with a full pitch, and its schematic diagram of the stator and rotor with its winding diagram is shown in the next slide. So you can just see here how the typically with the 60-degree phase spread you have two coils in a one spread of A, then minus C, and then B, and then again minus A in the next pole pitch, and that's you can call it like a coils are 180-degree apart from, and you can see clearly how the winding distribution of single layer winding with the distributed winding in 2 slot. You can call it phase spread is 60-degree and the slot pitch is 30-degree, and as the coils of each phase are spread in 2 slots, so there is the effect of distribution with the consequence that the induced EMF is attenuated, and the distribution factor may easily be computed for the fundamental case to the 0.966. Now coming to double layer winding, the same illustration considered in the single layer winding case is taken for the illustration here. That is the 2-pole 6 slot 3-phase machine with the full pitch coils, and the bold lines indicate the upper coil side and double lines indicate the lower coil side in the slot, and it is assumed that each coil side has multiple conductor in the figure. Note that the phase spread is 120-degree and the slot angle is 60-degree. So in one double layer you can have either phase spread 60-degree or 120-degree. I mean here we can say the phase spread is typically like a 120-degree. So here we have a 2 slot, each phase each slot is 60-degree, so 2 slots are 120-degree. So double layer winding can have a return conductor. I mean typically in the same pole pitch. So you can have typically a 120-degree phase spread in a one pole pitch like as shown in the figure, and you can see how the coil is placed with the top layer and bottom layer and have a typically 120-degree phase spread like when you can have a 3 coils in a one pole pitch having 3 phases, which includes that. So the distribution factor for this machine is 0.866, while the triple and harmonics distribution factor have become 0, considering the same machine for the fractional pitch winding having a coil pitch of 120-degree and the phase spread is the same as the coil pitch, and the schematic layout and the winding diagram for this case are shown in the next. You can clearly see here how it is in the typically for double layer winding. In the next you can call pole pitch as part of the return conductor in top layer and bottom layers like so. Double layer windings with the fractional pitch winding, the layout and winding diagram. So the distribution factor for this is 0.866 and the pitch factor also is the same as that of result. The winding factor is reduced to 0.75, whereas the machine double layer full pitch coils have a winding factor of 0.866 and the harmonic winding factor becomes different, and they are all considerably attenuated in the present case. So it is unusual to have low number of slots per pole per phase in the synchronous machines, but not in the brushless DC machine, such as illustrated case, but the basics that are covered here are easily extended to such high slots per pole per phase cases. Now coming to PMSM, fundamental design relationship. So now this section and other that follows consider some fundamental relationship relating to induced EMF, torque and power to machine and magnet dimensions, excitation current and flux density, leading to the physical understanding of the machine. And output power equations is also derived to enable sizing of the machine. An equivalent stator current induced magnetic field to match rotor field due to the PMSM magnets is derived to use the equivalent circuit of the PMSM. And the key to all the derivation is the air gap flux density, and it is affected by slotting of the stator luminescence, and it makes the air gap flux non-uniform, and the effective air gap to account for such non-uniformity is the introduce a correction factor to the physical air gap, and the effective air gap is slightly different from the actual air gap. So effective air gap considered the effect of slotting in a stator core is that the flux density in the air gap across the slot and tooth are very different, and therefore the air gap flux density decreases on an average due to the slotting of the stator core compared to the cylindrical surface without any slot. So according to reflect that in calculation, the air gap is modified from that of actual air gap by a coefficient known as Carter coefficient, and it expresses the ratio between the flux density in the air gap without slotting to the flux density with the slotting on the stator core, and Carter coefficient determined by the slot width Ws and the tooth width Wt and the air gap length Lg, and they are shown for a small part of the machine in the next slide. So as you can see here, the rotor is smooth, but the stator, you have a length of air gap here, and then you have a typically width of the stator slot and your width of the teeth and width of the slot Ws as a illustration of part of the core. So for the effective air gap, for one-sided slotting, that is the slotting of stator core only, effective air gap is GD equal to C into your Lg, and Carter coefficient C is given by C equal to Ws plus Wt divided by Ws 1 minus sigma plus Wt equal to 1 upon 1 minus sigma Ws upon Ws plus Wt, where the sigma is equal to pi in bracket tan inverse Ws upon 2 Lg minus Lg upon Ws logarithmic 1 plus Ws upon 2 Lg square, and typically total bracket close. So if these two equations, note that the ratio between the slot width and the air gap and ratio between the slot width and slot pitch are non-dimensional, and hence they are used in the plot of Carter coefficient shown here. You can see C is the Carter coefficient which varies on your width of the slot divided by length of air gap for slotted stator and PM rotor, and it varies, Carter coefficient varies over typically the wide range. So the slotting effect of the rotor is negligible in the case of magnets, as the air gap flux density is mainly due to the magnets, and the majority of flux is confined through the magnet rather than through the iron, separating the magnets and may be considered a tooth in the rotor, and this may not be justified in the rotor with the large number of magnets, as well as in case of interior permanent machines. And similar to the stator slotting effect, the rotor slotting can be accounted if necessary. So now coming to sizing procedure and main dimension. So coming to volume of all PM used in the motor, Vm equal to 2ph hm omega m into Lm. So depends on the quantity of permanent material maximum energy, where the 2p is the number of poles and hm, wm, im are the height, width and length of permanent respectively. So the output power of a PM synchronous motor is proportional to your Vm. So here it is, we can call it using the operating diagram of permanent. In second coordinate is given here. So diagram of PM for finding the origin of the recoil line and operating point. So you can call it the maximum electromagnetic power developed by a PM synchronous motor can be expressed as follows: Pmax equal to pi square by 2 into eta divided by kf kd 1 plus eta f br sc into Vm, where the kf equal to 0.7 to 1.3, the form factor of the rotor excitation flux, and kd is the direct axis armature reaction factor calculated by using kd equal to kfd divided by kf, where kfd is the ratio of first harmonic amplitude to the maximum value of normal component of armature reaction magnetic flux density in the d-axis, and kfd equal to bad1 upon bad. So here you can call it the form factors of the armature reaction for the PM synchro machine are given in the following table. You can see here the rotor configuration of the d-axis and q-axis. Typically the form factors are there for interior set PM rotor, surface mounted rotor, then surface rotor with the mild steel PM steel, then buried magnet, and silent pole rotor with the excitation winding. So here it is on the form factor of armature reaction for the PM synchronous machine. Now the peak values of first harmonic BAD1 of the armature magnetic flux can be calculated as a coefficient of Fourier series. BAD1 equal to 4 upon pi 0 to 0.5 pi b as a function of x cos x into dx, and kx is the form factor of the excitation given by kf equal to bmg1 upon bmg, where bmg is the magnetic flux density under the pole and bmg1 is its fundamental component. So coefficient of utilization of permanent in synchronous motor is defined as eta equal to EF IAK upon ER IAC equal to 0.3 to 0.7, and IAK is the current corresponding to MF FK for the point K as shown in the figure typically, and the point K is the intersection of the point of demagnetization curve phi equal to F as a function of capital F and the straight line. So G external equal to phi K upon Fk, and Gt equal to phi K divided by Fk minus F add max dash. In general, the current IAK is the highest possible armature current which take place at reversal, that is IAK equal to IA reversal, and the EMF ER correspond to BR, and the armature current IA correspond to SC. So with the aid of overload capacity, K of equal to P max upon P out, where P out is the output rated power, P max equal to 2 approximately twice of P out. The volume of permanents is Vm equal to Cv, P out upon FBR SC, where Cv equal to CO F KdF 1 plus eta upon pi square, eta equal varies from 0.4 to 3.1. So the inner stated diameter D1 in can be estimated on the basis of output coefficient for AC machine. So apparent electromagnetic power consists crossing the air gap is L ALM equal to M1 EF IA, that is pi root 2 F N1 K omega 1 F IF M1 pi D1 AM divided by 2 M1 under root 2 N1 equal to pi square by 2 NSP KW1 LI D1 N square by P PMG AM equal to 0.5 pi square K omega 1 D1 in square Li NS BMG AM, where NS equal to F upon P the synchronous speed and KW1 is the stator winding factor. So AM is the peak value of the stator line current density as per AM equal to 2M1 root 2 N1 IA upon pi D1 in equal to M1 under root 2 N1 IA upon PT and P tau and M1 root 2 N1 J SA P into tau, where J is the current density in the stator armature conductor and SA is the cross section area of armature conductor including the parallel wire. M1 is the number of phases, N1 is the number of the turns per phase, IA is the RMS current, armature current, and D1 is the stator inner diameter. So for air cooling system, J should be less than 7.5 ampere per millimeter square, sometime up to 10 millimeter per ampere. For liquid cooling system, it can be J can be between 10 to 28 ampere per millimeter square. So BMG is the where BMG is the peak value of the air gap magnetic flux density, approximately equal to the peak value of the first harmonic BMG1, and the amplitude of stator line current density AM ranges from 10,000 ampere per meter for small motors to 50,000 ampere per meter for medium power motors. So the electromagnetic torque TD equal to S ELM cos psi divided by 2 pi ns, that is equal to pi upon 4 KW1 D1 in square Li BMG Km cos psi. It has been assumed that BMG equal to BMG1 since P out equal to P in into eta M1 V1 IA eta cos phi, that is 1 upon eta SLN eta cos phi. The output coefficient is sigma P equal to P out eta divided by D1 square LINS equal to 0.5 pi square KW1 AM BMG eta and cos phi. So the air gap magnetic flux density BMG equal to phi upon L phi tau into Li. For sizing procedure for NDFBB PM synchronous motor can be initially estimated BMG equal to 0.6 to 0.8 BR. For the Faraday it is 0.4 to 0.7 BR. So there is a free choice in the effective length Li of the armature stack, that is the ratio Li in divided by D1 in depends on the motor application. So air gap mechanical clearance between the stator core and the rotor poles or pole shoe is advised to be 0.3 to 1 millimeter for a small permanent synchronous motors, and the smaller the air gap, the lower the starting current. On the other hand, the effect of armature reaction and cogging return torque increases as the air gap length of air gap decreases. So MF AD dash is the direct D axis armature reaction, F acting directly on the PM. So F AD dash equal to F EXCD 1 upon eta LM equal to M1 root 2 pi upon and root 2 upon pi N1 KW1 upon P KAD IAD 1 upon eta LM, where F EXCD is the direct axis armature reaction, MF refer to the field excitation system, and sigma LM is the coefficient of permanent leakage flux, N1 is the number of armature turns per phase, and IAD is the direct axis armature current. So MF F1 AD is the direct Axis armature reaction acting directly on PM, that is FAD dash equal to Fx second 1 upon lambda equal to M1 root 2 upon pi L1 KW1 P KAD IAD 1 upon lm, where FXD is the direct axis armature referred to the field excitation is the coefficient of PM leakage, N1 is the number of armature turns per phase, IAD is the direct axis armature reaction. Now coming typically on the effect of magnets or induced EMF, the magnet thickness or sometimes referred as magnet length, which is entirely different from stack length, its arc or width and its operating flux density are the variables that play a crucial role in the determining the air gap flux density and the induced EMF. The effect of magnet thickness on the operating point to find out the magnetic flux density has been considered in earlier section. So the effect of other two variables, magnet arc and the magnetic flux density on the induced EMF, is now derived. So here you can see air gap flux density for surface mount magnet machine. So consider the magnet has a arc of 2 beta in the machine. So its flux density will have a constant magnitude of Bm over 2 beta in the positive half cycle and minus 2 beta over the 2 beta in negative half cycle as shown for the surface mount magnet rotor as shown in the figure. So the fundamental of the air gap flux density, which is the sinusoid, will have a peak Bm1 obtained by the Fourier analysis Bm1 equal to 4 upon pi Bm sin beta, and peak induced EMF is Em equal to 2 pi f S TPH KW phi m1, where phi m1 is the peak fundamental flux in the machine. So now coming to peak fundamental flux density given phi m, peak fundamental flux is given phi m equal to Bm 1 pi dl upon p by 2, and where the d is the bore diameter as you can see in the figure, or the inner diameter of the stator lamination, L is the effective length of the stator lamination, so assemble as a stack. So now substituting the peak flux density in terms of the magnet flux density in the flux equation, and then using that in the induced EMF equation gives Em equal to 4 upon pi kW TPH dl Bm omega m sin beta. This equation describes the induced EMF and is its relationship to the machine dimensions, winding turns, magnet flux density and the magnet arc and the rotational speed. Now coming to electromagnetic power and torque. So if Em is the leading the rotor flux by 90 and the stator current leads the rotor flux by delta, known as a torque angle or power angle, then the real air gap or electromagnetic power is given P equal to real part of 3 Em Im conjugate under root 2 into root 2, and that is real 3 by 2 Em at the angle of 90 degree and Im at the angle minus delta, that is equal to 3 by 2 Em Im sin delta equal to 3 by 2 4 by pi Km TPH dl sin beta equal to Bm Im omega sin delta. So the real part of the three-phase power when the phasor power is the product of the RMS induced EMF and the conjugate of the RMS current given as. So from which the torque is derived T equal to P upon omega, that is 3 by 2 4 by pi K into K omega into TPH dl Bm sin beta Im sin delta, and equal to 3 by 2 dl 4 upon pi K omega TPH Im Bm sin beta into sin delta. So in this case torque can be written as T equal to 3 by 2 dl Bm sin beta into NSIS Im sin delta. So torque is determined by the product of bore diameter and the stack length, MMF, magnetic flux density and the magnetic arc angle, and finally the control angle between the rotor and current phasor. Now coming to typically electrical machine designer has control over the bore diameter, stack length, magnet flux density by the choice of the magnets and its arc and the number of windings per phase. And power electronics designer cooperate with the machine designer in choosing the number of turns based on the phase voltage that can be delivered from the inverter and its AC or DC supply. And the control system designer typically controls the magnitude of the current and the torque angle delta to deliver the specified torque at various. And this here is the T equal to 3 by 2 dl Bm sin beta NS Im into sin delta. So three are the different components to decide the typically electromagnetic torque here. An alternate form of the torque expressed as an interaction of the stator and the rotor, in this case magnet. MF is more fundamental than the derivations, and that is derived as follows. So peak fundamental magnet flux density can be expressed in the form of magnet MF as Bm1 equal to mu 0 Fm upon Gd, and where Fm is the magnet MF and Gd is the effective air gap length in the magnet axis. So the peak fundamental flux density is expressed in terms of the remnant flux density as given here. Bm equal to Br plus mu 0 mu rm hm equal to Br minus mu 0 mu m hg lg upon lm, or equal to Br minus mu rm lg upon lm into mu 0 hg, or equal to Br equal to mu rm lg upon lm into bg, and for that magnet operating flux density is required to derive as Bm equal to Br lm upon mu rm divided by Clg plus lm upon mu rm equal to Brm Br into lm upon Gd into mu rm, where the C is the Carter coefficient for correcting the air gap of stator slotting effect. So the relationship between the magnetic flux density and fundamental flux density is shown here, as you can see that typically in the diagram, and the flux density can be substituted from the in terms of the magnetic MF in torque expression at equal to 3 by 2 4 by pi k WTPS dl sin Bm sin beta into Im sin delta, and that is equal to 2 dl into p by 2 into 3 by 2 k omega TPH Im upon p into 4 by pi Bm sin beta into sin delta, and that is equal to 2 mu 0 dl upon Gd into p by 2 into Fs into Fm into sin delta. As you can see in the diagram, how the quantity are defined. So the torque representation now is the cross product of stator and rotor MF and containing the crucial physical dimensions given by bore diameter, stack length, and air gap, and number of the poles in the given machine. So that is typically here that equal 3 by 2 4 by pi kW TPH dl Bm sin delta into Im sin Bm sin beta into Im sin delta, and that is 2 dl p by 2 3 by 2 kW TPH Im upon p into 4 upon pi Bm sin delta into sin beta, and that is equal to 2 mu 0 dl upon Gd p by 2 Fs mm sin delta, where Fs is the peak value of resultant stator MF per pole, and derived earlier as Fs equal to 3 by 2 kW TPH Im upon p into L3. However, it is preferable by the designer to use a torque or power deriving equation within terms of linear current density and the air gap flux density due to magnet and the machine board volume, which lends to itself to the initial design process in sizing the machine very quickly with very free calculation and to the well-known machine power output equation. To consider the definition of linear current density and the ampere conductors per meter of board periphery with the current considered in RMS value. Here the total number of conductors in three-phase machine is 3 into 2 pH, as each turns have a 2 conductors, and AS equal to 3 into 2 pH divided by 2 pi r into IS, that is ampere conductor per meter, and it is distributed by stator around the periphery of 2 pi r meters, and hence the linear current density is defined as AS1 equal to kW into S into kW into 3 2 pH TPH IS upon 2 pi r ampere conductor per meter, accounting the winding factor only considering the fundamental value of the linear current density. Now substituting the MF in terms of linear current density in the torque yields it typically T equal to 3 by 2 4 by pi kW TPH dl Bm sin beta into Im sin delta 3 by 2 dl kW TPH IS under root 2 4 by pi Bm sin beta sin delta, and that is equal to 3 by 2 root 2 2 RL 2 pi r upon 6 into S1 Bm1 sin delta, or equal to 2 root into root 2 RL pi r AS1 root 2 BMR sin delta, or equal to 2 pi r square L BMR AS1 sin delta, where BMR is the RMS value of Bm1 and given as BMR equal to Bm1 upon root 2. Now the force generated is obtained from the torque expression. So F equal to TR upon R, that is 2 pi RL BMR AS1 sin delta in Newton, and the force density linking the force and surface area FD equal to F upon surface area, that is F upon 2 pi RL, that is BMR AS1 into sin delta Newton per meter square. So now electromagnetic torque multiplied by the mechanical rotor speed in radian percent gives the electromagnetic power known as air gap power output of the machine. So therefore the air gap power of the machine is then P equal to omega T, that is 2 pi r square L into omega m BMR AS1 into sine delta. So in some of the modeling of the PMSMs, the PMs are represented by current source, and this led it to use the existing models of conventional synchronous machine with the wound rotor with ease, and further this provides a way to relate the calculating the demagnetizing current for the magnet. So the equivalent magnet current, magnet is modeled as a current model with the RMS current IME as follows, and the peak fundamental magnet density is Bm1 equal to 4 pi Bm sin beta, and this can be assumed to be produced by equivalent three-phase winding of TPS turns per phase, very similar to the stator, to counter the magnet flux density, and its MF equal to Fm equal 3 by 2 TPHI MEP upon P, where MEP is the peak current, and the peak fundamental magnet flux density then given Bm equal to mu0 Fm upon GD, that is mu0 3 by 2 root 2 IME TPH GD P equal to 4 upon pi Bm sin beta, where Bm is the flux density, magnetic flux density, and GD is the effective air gap. And equivalent magnet current in terms of RMS value IM equal to 4 2 upon 3 pi GD PBM upon mu0 TPH and sin beta. So the magnet operating flux density can be calculated as before, as Bm equal to Br in bracket Lm upon mu Rm divided by C Lg plus Lm upon mu Rm equal to Br Lm upon Gd into mu Rm. So substituting for the air gap along the magnet axis, Gd is the magnet equivalent current expression, and the magnet equivalent RMS current in terms of the remnant flux density, edge winding turns, magnet length, and magnet R is obtained. IM equal to 4 upon 3 pi PBR Lm upon mu0 mu R TPH into sin beta. Coming to safe peak stator current, the peak stator current is determined by the maximum current that will not demagnetize the magnet, and that is not allowing the operation to the slide into the nonlinear part of the demagnetization characteristic, as shown below the boundary being that between the linear and nonlinear operating point HP and BP, as shown in the typically in the figure. So BH characteristic, is BP equal to mu0 mu R HP plus PR. So stator current that can produce a flux density to counter this may be assumed at ISP, and that is the peak current. So M by ISP equal to FSP 3 by 2 TPH IPSP upon P, and considering the path of the flux through magnet stator iron and the 2 air gap, the MF in this closed path is 0 and written as 2 HCLM plus FSP plus HG in bracket GD plus LM upon mu R equal to 0, and at peak operating condition the air gap flux density is given Hg equal to Bp upon mu0. So peak allowable flux density just before demagnetizing, assuming the linear magnetization is given as Bp equal to Hp minus Hc into mu0 mu R, and then the air gap flux intensity field intensity is Hg equal to Hp minus Hc into mu R, and from the MF relationship the safe stator peak MF is defined FSP equal to Hc minus Hp into mu R, and GD multiplied GD plus Lm upon mu R minus Hc into Lm equal to 3 TPH upon 2P into ISP, and then the RMS value of maximum stator current is derived as ISM equal to ISP upon root 2, that is root 2P upon 3 TPH in bracket GD mu R Hc minus Hp minus Hc into Lm, and this current is the absolute maximum that machine can subjected to all under all circumstances. Now coming to core losses, the core losses are not negligible in permanent synchronous machine and brushless DC machine. Only stator core losses are being dealt in the treatment, and the rotor core losses are not taken up for the simple reason that ideally there are no flux reversal in the back iron, and therefore no significant losses can occur in it and is in the small teeth section of the intrinsic between the magnets facing the air gap. So then it is incorporated during the fine tuning of the final design, either analytical or finite element analysis technique, and for computation of rotor core loss strictly in the iron, the approach for the stator core losses computation may be gainfully used, and as for the pole phase losses, it is entirely a different issue, and it is left to the reader to dwell into in existing literature and in-house design procedure. But such is not the case in case of high-speed applications, for it not only has the core losses but also has the pole phase losses due to the current harmonics injected into the stator winding which get reflected on the magnet, usually for low speed machines with the low pole numbers. It is not unusual to ignore them for initial design or sizing. So now coming to stator core losses, the core losses in the machine have two components, hysteresis and current losses, and the core losses occur due to the time variations in flux density experienced in the core, and the hysteresis loss is the result of inherent pH material characteristic and is proportional to the product of frequency and flux density with the flux density raised to a power n, generally termed as Steeman's constant. And when the lamination core experiences a change in the flux density because of a change in the flux and hence the flux linkage, note that the flux is equal to the product of the flux density and the area of cross section of the core, and as the flux linkage changes with the time, the cores have an induced EMF induced in them. So the induced EMF generates a current in the core depending upon the resistance of the core, resulting in the losses that are termed the eddy current losses. And to evaluate the eddy current losses, it is important to find the induced EMF in the core and hence the necessary to calculate the flux density in the various parts of the core. So eddy current losses are also the proportional to the square of the induced EMF and hence the proportional to square of the product of frequency and flux density. So thus the eddy current loss is equal to PED proportional to F BP square proportional to omega S BP square, and which can be written as PED equal to KE into MSC square BP square weight per unit weight, watt per unit weight, where K is the loss proportional constant that accounts for the volume to weight conversion and all the other particular constant associated with the magnetic material, and B the peak flux density and fundamental angular frequency of the applied voltage is omega S. So the steel manufacturer provides the eddy current loss per unit weight, say watt per kg, versus peak flux density for the various frequencies as shown typically in the figure. So from these manufacturer graphs and data, the eddy current loss proportionality constant can be computed for a given flux density and the frequency. And the hysteresis loss in general can be represented in watts per unit weight, say watt per kg in line with the manufacturer data sheets. So PH equal to KH omega S B to power n watt per unit, where KH is the hysteresis loss density proportionality constant and n is the H is known as the Steeman's constant. So the value of n ranges from 1.5 to 2 and is dependent on peak operating flux density and material characteristic. So total core loss per unit weight, which is the core loss density, is the sum of the eddy current and hysteresis loss component and is given as PCD equal to PhD plus PED, and a partial surface mounted PMSM is shown here for illustration of flux density in the machine. So you can just clearly see how it is typically surface mounted PMSM details for core loss computation. From no load tooth and back iron of yoke flux density are shown here in the diagram, and tooth and yoke flux density waveform are shown here as a different waveform. So now coming to flux density have finite change and do not have a discontinuity as shown in approximated diagram, but will rounded off with the smooth changes in the corner. And note that the rotor flux density does not undergo changes and hence ideally the rotor core losses are non-existent, and therefore the core losses occur in the stator iron alone. Note that there are rotor pole phase losses due to the stator time harmonic fields produced by the stator excitation. So for the present, these losses are ignored in this treatment. Now coming to eddy current losses occur in the stator teeth and back iron of the stator, and the effect of rotational losses due to the rotation of the flux density in back the teeth is yet to be fully understood and documented. So therefore, for this matter, it is not considered in this chapter. The eddy current losses have been traditionally derived assuming a sinusoidal flux density, and the average eddy current loss is calculated as follows. So let the instantaneous flux density part of iron B equal to BP sin omega st, and at its rate change is given delta B upon dt equal to omega s BP cos omega t, and the average eddy current loss density is then given by dB upon dt square AB2 square average 1 upon 2 pi 0 to 2 pi dB upon dt square into d upon omega st equal to omega s BP square upon 2 pi 0 to 2 pi cos square omega t d omega st, and that is equal to omega s BP square by 2 into watt per kg. So substituting for the square of the product of the frequency and peak flux density, PD equal to KE omega s square BP square watt per unit weight, And in terms of eddy current losses, density and its proportionality constant, the right hand side is dB upon dt omega is dB into cos omega t, and the eddy current density in terms of the rate change of flux density derived Pd equal to Pi dB upon dt square into watt per kg. So from the earlier flux density plots, it can be seen that the rate of change of air gap flux density is marginally affected for this particular torque angle as compared to the operation with the torque angle other than 90 degree. In interior PMSM and even in the surface mount PMSM, there is a great advantage in operation with the torque angle greater than 90 degree. So then, under these circumstances, the simplified analysis for eddy current loss and hence the core losses calculation may not hold. So in spite of such shortcoming, the analytical method has the benefit of relating the machine dimensions and variables to core losses, providing an insight into core loss reduction during the design stage of the machine itself with the appropriate machine design changes. So the steel manufacturer gives the core loss the density data in terms of watt per kg and corresponding with the data sheets, and core loss can be represented as H equal to TPHI upon LM, where BM is equal to BR upon 1 upon plus mu RM LG upon LM into M upon LG 1 upon K in bracket 1 minus HE upon HC equal to B0 in bracket 1 plus HE upon HC, and P equal to rho I into V into PD, and that is rho I into V Ke omega BP square equal to rho I V into 2Ke dB upon dt square average in watt, where Pi is the mass density of the steel core material in kg per meter square, V is the steel core volume in meter is cube, and their product given gives the weight of the core material in kg. Now coming to eddy current loss, in the following eddy current losses in the stator teeth and yoke are derived first and then hysteresis loss is estimated. Both of them require computation of peak tooth and yoke flux density, which in turn are computed from the air gap flux density, and the calculation of loss coefficient is also discussed here in brief, and core losses measurement is introduced to enable ingenious Planck experiment. So here the tooth flux density rises from 0 to peak value BTP shown here, and leading edge on the rotor magnet, and says the north pole passes to the south pole. Now when the tooth is fully covered by the magnets, its flux density does not change and hence remains constant as BTP until the magnet trailing edge start to leave the tooth when the flux decreases from BTP to 0, and similarly the case when for the south pole passing by the tooth, but its flux density is of opposite polarity and its shape is identical to that of previous case, and the time taken for the tooth flux density to change from 0 to its peak value Tt is given by Tt equal to width of the tooth rotor velocity, that is omega t Wt upon r omega or Wt p by 2 r omega s, or Pt p omega t upon 2 rs omega s, where r is the air gap radius and omega m and omega s are the mechanical rotor and electrical angular frequency respectively, and omega t is the tooth width. Now the rate of change flux density then is given by dB upon dt, that is Btm upon Tt, that is 2 r omega s upon p into Wt Btm. In one electrical cycle, it is seen that there are 4 such variation in the flux density, and during these time eddy current loss occurs, and time duration for which the eddy current loss happens the fraction of fundamental electrical cycles, and expressed in terms of eddy current loss duty cycle is into derived as d equal to 4tt upon ts equal to 4 p Wt up to W mrs upon 1 upon Fvs equal to 2 p Wt Ws upon R Ws into pi equal to p Wt upon pi r, and therefore the eddy current loss in the tooth can be written as Pet equal to pi rho I into Vt in bracket 2 Ke dP upon dt square into dt, that is 8 Ke pi rho I Vt upon pi r upon p Wt into omega e Wtm square in watts, where rho I is the mass density of the tooth steel given in kg meter cube, and Vt is the volume of the teeth in meter square. Now eddy current loss in the tooth. Note that the rate of change of flux density and duty cycles are substituted in terms of machine dimensions and variables to yield the final expression. So it can be seen that eddy current loss can be reduced significantly by varying the rate of change of flux density in the teeth. So it can be achieved in 2 ways. First is the shaping the rotor magnets, and second such as an action has the effect on making the flux density sinusoidal, which in turn has lower rate of change compared to the trapezoidal tooth flux density, and then the eddy current loss amounts to P equal to ETS equal to KE y Vt omega s Btm square in watt. Now coming to typically second, optimization of number of slots and tooth slot width. So decreasing the slot number per pole and making the slot width equal to the tooth width reduces the eddy current loss nearly to that of the loss with the sinusoidal flux density, tooth flux density. And as the number of the slots is made close to the number of poles, the tooth flux density becomes closer to the triangular wave with a smooth top of a sinusoid. So, the effect of optimizing the slot number and slot opening is demonstrated as follows. So, let NS be the number of slot per pole and the width of the slot is Ks times the width of the teeth, and then the tooth width is related to the air gap radius, that is 2 pi r equal to NSP P in bracket Wt plus Ws equal to NSP P 1 plus Ks into Wt, which on substituting eddy current loss equation results in PET equal to 4 Ke rho I Vt upon pi square into NSP into 1 plus Ks into Ws Btm square or equal to Ke Pi rho I Vt Ws Btm square equal to 4 upon pi square NSP 1 plus Ks or equal to K Pts equal to 1 upon in bracket 4 upon pi square NSP 1 plus Ks. So, where PETS is the eddy current loss in the tooth with a sinusoidal flux density, and the ratio of the eddy current loss between the trapezoidal and sinusoidal flux density distribution then derive is Pt equal to Pts 4 upon pi square NSP 1 plus Ks. So, this shows clearly that eddy current loss in tooth can be made equal to that of sinusoidal flux density case if the number of slots per pole is reduced close to 1. Now, the effect of the slot per pole at the ratio between the slot and the tooth width on eddy current loss is shown here. You can see how it is varying with the NSP. So, tooth eddy current loss ratio with number of the slots per pole, ratio of slot to width ratio. Now, machines with higher slots per pole and trapezoidal flux density in the teeth have multiple times the eddy current loss of the machine with sinusoidal flux density distribution in their teeth, and higher number of slots per pole is preferable to obtain the nearly sinusoidal induced EMF in the machine phases, but it is highly undesirable considering the tooth current eddy loss. So, the flux density eddy current loss in the yoke. The flux density in the yoke is approximated as a trapezoidal waveform as shown here, and consider a point on the yoke. So, as the north pole comes towards the flux to it, the flux density is falling from the maximum value B by M to 0, and when half of the rotor magnet pole arc passes this point, then for the other half of the pole arc passing, the flux density falls from 0 to negative maximum, that is B minus B by M. So, after that, flux density remains constant at B by M until the south pole of the magnet comes across the point. So, therefore, the time taken for the flux density to rise from 0 to B by M is derived as Ty equal to half width of the magnet divided by rotor velocity, or Wm by 2 divided by r omega m, or equal to 2 beta r by 2 into b by 2 divided by r omega s equal to beta p beta into 2 omega s. The 2 beta is the magnet arc in electrical degree. Now, the total time for flux density changes is 4 Ty in 1 electrical cycle, and then the rate of change of flux density therefore is given by using above equation as d V by upon dt equal to V by m upon Ty, or equal to 2 P by m omega s upon P b beta. The eddy current loss in yoke then given as P E y equal to rho I into V I P y in bracket 2 K 4 Ty upon Ts dB dy upon dt square, average of it equal to 2 Pi Vy in bracket 8 upon pi b omega s B by m square. And compared to the central flux distribution eddy current loss, the trapezoidal yoke flux density based eddy current loss can be derived as Pey n equal to Pey upon Pys Ke rho I Pi Vy in bracket 8 upon pi beta omega s beta by m square divided by Ke rho I Vy omega s P by m square into 8 upon pi beta. And the normalized yoke eddy current loss versus magnet arc is shown here typically. And see normalized curve eddy current with the graph. So, now coming to evaluation of peak tooth and yoke flux density. The maximum flux density in the teeth and yoke are evaluated from the residual flux density and the average flux density. The average air gap flux density can be derived from the residual magnetic flux density using the permeance coefficient of the magnet circuit explained earlier, and let G be the effective air gap length on the magnet axis, taking into the account the effect of slotting with Carter coefficient. Now, then the average air gap flux density is derived as Bg equal to Vr upon 1 plus mu Rm G upon Lm, and the peak tooth flux density neglecting fringing can be approximated by making use of the fact that the air gap flux over the slot pitch enters the tooth and is carried out in it given as BTM equal to Wt plus Ws by Wt into Vg in Tesla, where Wt and Ws are the tooth and slot width respectively. So coming to now, typically similarly the peak yoke flux density is found by equating the air gap and yoke flux obtained multiplying the air flux density with their respective area of cross section at Bym equal to omega m Wm upon 2 By into Bg in Tesla, where Wm is the width of the magnet and By is the back iron thickness. Now coming to hysteresis loss, the hysteresis loss of the teeth and yoke of the hyster are found using the following relation: Hs equal to Kh into rho I in bracket Vt Btm n to power n plus Vy into Bym to power n into omega s in watts, where Kh is the hysteresis loss density, n is the estimated constant, and this hysteresis loss, they together with the Ke are obtained from the magnetic steel manufacture data by using the general core loss density formulation, that is PCD equal to PhD plus PCD, that is Kh omega s Bp power n plus Ke omega square Bp square in watt per kg, and the constant may be extracted from the curve fitting from the given data from the manufacturer as shown in the figure. Now, coming to this history, it is not unusual to design the machine for frequency at which the manufacturer core loss data may not be available. So in that case, an experimental setup to measure the core loss of the eliminations at desired frequency is now available. So accurate determination of core losses is very crucial for high-speed machine designs, and it will be much more significant that of other losses in the machine. Now coming to core loss measurement in the machine, the test machine requires an auxiliary motor to drive it in this method. So no load loss of the auxiliary motor is measured by running it alone, and its input power is measured for each speed, as copper losses are evaluated separately. Then the test machine is coupled to auxiliary motor and driven on no load with the stator windings open circuited, and typically you can see how electric motor testing diameter. So typically the measuring the torque output of the auxiliary motor and multiplying with the rotary speed give the test machine core friction and windage losses. So now coming to core loss measurement in the machine, to separate the core losses and friction windage losses of the test machine, the test machine rotor is replaced with the identical test machine rotor but without the magnet on it. It's filled preferably with the equivalent non-magnetic material of the same weight in place of magnets and driven by the auxiliary motor, repeating the measurement, and the measured power output of the auxiliary motor gives the friction and windage losses of the test machine. Now coming to resistive losses, stator windings produce losses whenever they carry a current, so they are referred in common parlance as copper losses. So given the rising cost of copper, many new products may have used aluminum in not too distant future, and hence it may be better to retain the term resistive loss hereafter. So the resistance per phase winding is computed from the number of turns TPH, material specific resistivity rho, average length of the conductor LC, and that is half of the winding turn, and area of the cross section area of the coil AC by computing the resistance of one conductor and then multiplying it with the total number of conductors. So RS equal to rho LC upon AC into 2 TPH in ohms. Now resistance have to be corrected for both operating temperature and the frequency effect of sinking skin depth and its attendant increase in value. So resistive loss for a 3-phase machine with stator RMS currents of ISR PS equal to 3 IS square RS into equal to 3 rho IC square AC square into LCAC into 2 TPH equal to 3 rho JC square VC in watt, and where JC is the conductor current density in the coil, VC is the volume of the winding material, and B its copper or aluminum. Volume of material is given as VC equal to LCAC into 2 pH in meter cube, and JC equal to IS upon AC in ampere per meter square. The implication of stator resistive load expression is that it shows a fixed volume of winding material, varying the number of turns per force reduces the conductor area, increases the current density, and inevitably the resistive losses. The outcome will require thermal redesign to address the issue as well as reduction in the machine efficiency, which has become a premium requirement recently. So, in comparing machines, particularly in industrial setting, it is crucial to maintain volume of winding material apart from the other variable constant. So, note that the expression for stator resistive losses and its implications are applicable to all electrical machines except the number of phases had to be modified in case of other machines than three phases. In design optimization, it is very useful to derive the resistive losses in terms of linear current density apart from the conductor current density, pore diameter, and stack length, so that common terms can be found between it and the power output expression in the machine. So, now specification of resistive losses as a percentage of power output for a design optimization leads to an use of both the power output and the resistive loss expression. So, in tune with that, resistive losses are reformatted as PS equal to 3 IS square RS equal to 3 IC square rho LC upon AC into 2 PH in watt. But the length of one conductor of phase winding can be written for a distributed winding as equal to the stack length and 1/2 of the bit across the stator pole arc, which in turn can be written in terms of the bore radius. But the build can be very accurately estimated and can be taken as a constant for the specified number of turns and stator laminations and stack length. So, it is factored by a parameter A, and the length of one conductor is expressed equal to LC equal to in bracket L plus 2 pi R upon P into A meter. The factor A can handle all the cases of short pitch winding in case of distributed winding, and for concentrically wound machine, appropriate factor and the build width across the stator pole have to be modified. So, the stator copper losses then are PS equal to 3 IS square rho LC upon AC into 2 PH equal to 3 IS upon AC rho TPH IS into in bracket 2L with bracket 1 plus 2 pi R upon P into A in watts, and the stator MF can be expressed in terms of fundamental linear current density, and its definition as AS1 equal to KW1 3 into 2 PH upon 2 pi R into IS ampere conductor per meter. And substituting the for MF in terms of linear current density, the stator copper loss are PS equal to 6 JC AS1 rho 2 pi R upon KW1 in bracket L 1 plus 2 pi R upon P into A equal to rho in bracket 1 plus 2 pi R A 2 pi A upon BP divided by KW1 into 2 pi R square JC into S1 in watts, where L is equal to B into R, where B represents the ratio between the stack length and the bore radius. So, dividing the stator resistive loss by rated or output power, divide P equal to omega m T, that is 2 pi R square L omega m BMR AS1 sin delta in watts, expresses the stator copper loss in non-dimensional unit denoted as per unit. The total torque angle is assumed to be 90, as this is the reasonable assumption for all types of permanent synchronous motors. So, then the per unit resistive losses are given as PSN equal to PC upon PA, that is KR square JC AS1 upon 2 pi BR cube AS1 BMR omega MR equal to 2K upon 2 pi B into J upon BMR into 1 upon R omega R per unit, and where and K 2 pi P in bracket B plus 2 pi A upon P divided by KW1, where B omega R is the radius in radian per second in rated speed of the PM, and PSM is the normalized value of stator resistive losses. Now, coming to the PMSM numerical problems. Question 1. Compute the stator core losses versus speed in RPM. Using the analytical expression, the machine details are air gap radius R equal to 58.5 millimeter, stack length L equal to 76 millimeter, outer stator diameter DO equal to 95 mm, that is 2R0. Yoke thickness BY equal to 17.54 millimeter, tooth width equal to TH equal to 17.2 millimeter, and tooth width equal to W2 equal to 5.3 millimeter, effective air gap length 2 millimeter, magnet thickness LM equal to 6.3 mm. Now, magnet R2 beta equal to 120 degree, number of slot NS equal to 36, number of poles P equal to 4, air gap flux density V is equal to 0.79 Tesla, peak flux density PTM equal to 1.53 Tesla, peak yoke plug density BM equal to 1.2 Tesla, hysteresis loss density KH equal to 5.8 10 power minus 3, and eddy current loss density K equal to 9.3 into 10 power 6 minus 6, and instrument constant N equal to 1.93, and instrument mass density Ri equal to 7650 kg meter cube. Now solution: teeth volume is NS WT TH L, and that comes to 2.494 into 10 power minus 4 meter cube, and yoke volume, that is pi in bracket RGO square minus R plus TH square into L, that comes 7.866 into 10 power minus 4 meter cube. Magnet width is WM equal to R minus LM by 2 minus G by 2 into 2 alpha upon P by 2, that comes 0.0569 meter, and slot width is 2 pi R upon NS minus WT, that's 0.0049 meter. So the core loss versus speed is shown here for a maximum speed of 3000 rpm, corresponding to the hysteresis frequency of 100 Hz for the surface mounted PMSM. You can see the core loss, and note this reads typically coming from the sum reference. Now coming to question 2, find the main dimensions and volume of PMSM of a 3-phase brushless synchronous motor rated at output power of 1.5 kilowatt, input frequency 50 Hz, synchronous speed of 1500 rpm, line voltage is 295 volt. So Siemens cobalt PMM combinates with BR equal to 1 Tesla and S equal to 700,000 ampere candles should be distributed at the rotor surface and furnished with the mild steel shoes, and these poles can replace the cage winding and reduce the starting current, and the product eta cos phi at the rated load should be minimum 0.75. The motor has to be designed for continuous duty and inverter applications, and estimate the number of armature turns per phase and cross section of armature conductor. So coming to rated armature current, I equal to P out upon 3 V1 eta cos phi. So putting the value, it comes 3.9 ampere, and number of poles pair P equal to Fs upon Ns, that comes 2. Since the synchronous speed is revolution is 25, this is 4-pole motor. So for the same cobalt PM, it is recommended to assume the air gap flux density in 0.65 to 0.85 Tesla, say 0.75 BR, that is BM equal to 0.75 Tesla, BMG equal to 0.75 Tesla. The straight line current density for the 4-pole 1.5 motor should be approximately M equal to 30,500 ampere per meter peak value, and the winding coefficient for 3-phase 4-pole double layer winding can be used KW1 equal to 0.96. The output coefficient can be calculated rho P equal to 0.5 pi square into 0.96 into 30,500 into 0.75 into 0.700, that's a 81,276 V upon meter cube. So no load EMF to the cage voltage ratio has been assumed eta equal to 0.85. Then the product is D square L equal to rho I eta upon beta NS, putting value, it comes 0.000613 meter cube, and then the product D1 L equal to 613 centimeter cube. The correspond to inner stress diameter of D1 in 78 mm, and the effective stack length Li equal to 100 mm. So since the motor is designed for the variable speed drive inverter application, the main dimension has to be increased to D1 equal to 82.54 mm and Li equal to 103 mm. Then the pole pitch tau equal to pi d upon 2p, putting a value, which comes 0.0648 meter, and the alpha e 0.54 effective polar coefficient is BP equal to L tau, that is 32.4 millimeter. Since the surface magnets are furnished with the mild steel pole, so BP is the width of the external pole shoe. So thickness of the mild steel pole shoe has been assumed to be dP equal to 1 millimeter. So air gap in the D axis has to be chosen small, G equal to 0.3 millimeter, and similar as that of cage induction motor. So Q axis air gap can be much larger, say GQ 5.4 millimeter. The form factor of the armature D axis to the table on next slide is say KFD equal to 1 upon pi and bracket 0.5 pi sin 0.5 pi plus 0.8148 minus and bracket pi minus 0.5 pi into sin 0.5 pi, that is 0.966, where T dash G equal to 1 minus dP upon, and it comes 0.8148. So the form factor of the armature reaction for PMS synchronous machine are given in the table. From here, typically form factor are given for different potential, different type of motor. So form factor for excitation field is Kf equal to 4 upon pi sin alpha pi by 2, that comes 0.9, and armature reaction factor in D axis KD KFD upon Kf, that comes 1.074. The overload capacity factor has been considered OCF equal to 2, and the coefficient of utilization of PM can be estimated equal to 0.55. So then the CV, that is KOC, KF, KD 1 eta upon pi square theta, putting value it comes 1.303, and the volume of PM is estimated VM equal to CV P out upon F PR into SC, putting value it comes 56 centimeters cube, and 3 parallel 5 millimeter thick, 10 millimeter wide, and 100 millimeter wide surface ceramic cobalt permanganate per pole have been designed as shown in the figure typically. So here is the rotor of motor, dimensions, magnetic fluctuation. So volume of the all permanganate in the motor is Vm equal to 2p 3hm omega lm, and putting value it comes like a 60 centimeter cube, and the rotor has been built from the solid carbon steel. So surface SMCO ceramic cobalt permanganate have been fixed with the aid of special glue. In addition, each PM pole has furnished with a mild steel pole. So number of armature turns per phase can be rounded roughly chosen to the base of assumed line current density and armature current, that is N1 equal to M P tau upon M1 root 2 IA, that comes around 240. Double winding loaded S1 equal to 36 stator armature slot has been considered, and for 36 slot 2p equal to 4, the number of armature turns per phase will be N1 should be 240, and two parallel conductor with their diameter dA equal to 0.5 mm have been chosen, and the cross section area of the armature conductor is S equal to 2 into pi d square pi dA square by 4, that comes 0.3927 millimeter square, and the current density in the armature conductor J equal to I upon SA, that comes 9.93 ampere per millimeter square. This value can be accepted for continuous operation of a small motor, provided the motor is equipped with the fan and the insulation class is minimum F, and the motor specifications are given here along with in the table, all the specifications of the design motor. So coming to question 3, find the losses due to the 7th harmonics in 4-pole surface PM spinning at 10,000 rpm. The air gap is equal to 1.5 millimeter. The magnitude of magnetic flux density in 7th space harmonic BM7 equal to 0.007 Tesla, and the electric conductivity of NDF in PM is sigma PM equal to 0.5236 10 to the power 6 S per meter at 100 degrees Celsius, and relative permeability is 1.035. The magnetic polar to pole pitch ratio is alpha equal to 0.8, and the rotor polar D2 out is 0.1 meter, and length of PM equal to length of stack length LM equal to LI equal to 0.1 meter. So the pole pitch tau equal to pi D plus 2 DL by 4, that is 0.81 meter, and the parameter B7 is 7 pi divided by tau, that is 271.31 meter, and frequency of the stator current F equal to into NS upon 60, that's come 333.3 hertz of magnetic flux, and F7 equal to 1 minus, that's it, so that's come 2000 hertz, and this harmonic rotated at the same direction as rotor. The coefficient of attenuation 7th harmonic torque is K7, putting value would come 65.4 per meter. The coefficient ARV for 7th harmonic RT value come 4.156, and the age of coefficient for 7th and K7, that is putting a value which come 1.074, and the surface area of PM is SPM equal to value equal to 0.25 meter square, and therefore the loss due to the 7th harmonic is very delta CM, putting value comes here to 23.6 watt, and these are the references which are followed for the preparing this material, and thank you very much.